Hi, welcome to the Pole Shift News. It's Jim from the Mavestar Observatory. Guys, we have really opened a can of worms when we've started to look into the world of muons, and a bit later on I'm going to get into some of the implications we are going to face a little later on down the road. If you was with me in the video yesterday, I was looking at how we can scale cosmic muons, which are here on the surface, in the numbers according to other sources, around 10,000 per square meter per minute. So it's a lot, but we can really make a scientific contribution towards the science of at least muons, and informing the general public as to what they've got to expect. Because if you look at this, you can see that cosmic rays form 14% of the background radiation that we receive here on the surface of the Earth, and these are set to be on the increase. With the ongoing grand solar minimum, like I said, we've not reached the equilibrium of that yet, so this could go on for many years. And if that's the case, cosmic radiation is going to increase because of a weakened heliosphere, and in turn those cosmic rays are going to collide with atmospheric molecules and atoms in our atmosphere and produce muon showers. And if we're going to get an increase in muons, then at least we need to find out what the implications that lie with regards to health risks to ourselves as these increase. What you've got to remember is, guys, we've got something else taking place alongside the grand solar minimum and the shrinking of the heliosphere, allowing more cosmic radiation in. We've also got a magnetic pole reversal, and that in turn weakens our magnetosphere, and in turn allows more of that cosmic radiation inbound to our atmosphere. So the showers of muons are going to increase. Now, I'm not too pleased with the discovery I made yesterday, but before I get into that, what I really need to do is just thank those people that are supporting us at the Mavestar Observatory and the work that we're doing. I'm investing more and more time now into the research of muons, finding everything out I can about them, and there's a lot of unclear work that's not been done on these. They don't know, like for instance, you cannot get which I'm about to show you later on, a chart that shows you the level of risk with regards to radiation with muons, as opposed to what we already know about gamma, beta and alpha radiation. So a little bit later on I'm going to tell you what the implications are with regards to muons, and I don't think a lot of you are going to like it, but we're adults, we can angle the truth. And the main thing here is, guys, is that we say thank you to the people that are allowing us to continue at this point with the research, but we need more people to come on board and support what we're doing. At the end of the day, guys, we're trying to reveal to you what these organisations that are spending into some degrees over £1 billion a day, yes, £1 billion a day in this research with regards to cosmic rays. So what we've got is, like I've said before, the same level of detection equipment what they've got, and you've got a good all-round scientist that is able to fine-tune this equipment, improve it, and improve the accuracy of the measurement of the muons. All I need, guys, from you is a helping support and a push with some finance, and we can take this to the next level. There's going to be a lot of work ahead, and it's not just going to be building equipment and sending it out into the field and collecting that data. It's going to be the analytical part of that data, processing it and making some sense of it. And to do that, we've got to iron out all those uncertainties. I don't want to bore you guys with this, but I will say this: it has massive implications on all of our lives, and every day that goes on there is going to be an increase slightly in the cosmic radiation that comes into our atmosphere and collides with them particles and creates more of these muons. So I'm going to show you right now where we stand with how dangerous are muons. And just remember that at the end of this video, guys, there'll be a link there and you can help support us if you want. I really hope that a few more of you are encouraged by what I'm about to show you in this video. Okay, let's get on with it. Now guys, yesterday, if you joined me in the video, you'll know that I was trying to find a scale or comparison that we could compare with, common radiation such as alpha, beta and gamma, and we could possibly slide in the muon in that range, so that we could look at microsieverts as a level of scale of how harmful these muons are. But the truth of the matter is they're much worse than gamma radiation, and the reason for that is because muons travel at a lot greater speeds, they have bigger mass, and they even penetrate deep into some of the most deepest mines we have on this planet. So if we use a radiation chart as a level of how dangerous muons are, you've got to add to it, because you don't need so much gamma radiation in this case, or so much beta radiation as what you would do muons. Muons are much worse than gamma radiation because they simply pass through more of the denser material. If you look at alpha radiation, you can see that it can be stopped by the human skin or a piece of paper. But if alpha radiation does go beneath the skin, then it's very harmful to you. Beta radiation can be stopped by, as you can see, a thin aluminium plate. But gamma radiation can pass through concrete, steel, lead to a certain thickness. I mean, you've got to have a real big chunk of lead to stop gamma radiation. But unfortunately, guys, for us, muons go straight through the lot. And we don't know, whether it's twice as bad as gamma radiation, 3 times as bad as gamma radiation. We can only, at this point, do more research to find out what the case is. But what I can tell you is that it passes through more material than what gamma radiation does, and we know how serious gamma radiation is. So if we just look at a scale of microsieverts, millisieverts and sieverts, we can get sort of a gauge as to how much muons become harmful. What I'm saying to you guys is, like, we've got a scale only of gamma radiation, but we know muon radiation, if we're going to call it muon radiation, and we should do, because it's just it's in the same nature as gamma. In fact, some of our muon detectors do pick up gamma radiation. And I've come up with an idea of how to try and filter out the gamma radiation from the counts that we get on the muon detector. So let's have a look at then the levels of what at least gamma radiation are, and if we're getting more levels in sieverts than we are if we're getting more levels of gamma radiation in terms of sieverts, then when we look at muon rates, it's going to be much worse than that. So let's have a look at that rate. So if we look at the scale that the United Nations Scientific Committee have produced, we can see that from 0 to 20 millisieverts you get a very low dose. If we're talking about muons, it would probably be a stage higher, probably on the scale of probably 10. 1 millisievert would probably be 10 millisieverts. If we're talking about dosages of muons. So always remember is we can only go on what we have to hand at the moment, and that is radiation levels of common known radiation such as gamma, beta and alpha. If we was talking about muons, it would be a lot less quantities, would be more harmful. In a little while we'll go through just what all these millisieverts means in terms of actual exposure to some known radiation sources, such as in the reactor room of Chernobyl, we've got a reading for that, or Fukushima, etc. So that's the scale that we'll use for now. But if we're getting anywhere near the rates of muons that then all we've got to know is that if we're getting high rates of muons in the 200 to 2000, then it's probably going to be on the very high dosage. We won't need 10 sieverts of radiation to become very harmful. So let's have a look at what some of these from the United Nations Scientific Committee relate to. Now, before we go any further, don't alarm yourself, because there's a lot of things that affect radiation poisoning. What we're looking at now is just the lower levels of radiation that people experience. You can see from the top of this chart, just simply sleeping next to somebody, you can receive 0.05 microsieverts. If we look at the bottom of the chart, an airplane flight from New York to LA, you will receive an average dose of around 40 microsieverts. We'll put that into context, but what you've got to remember is there's a lot of things that vary in radiation poisoning of any sort, and that even includes our muons. It depends on how long you're exposed to it, and levels of it, obviously will impact the the danger frequency that you want to avoid. But just to put this in perspective, if we look at all what's in blue there, and you can see the different forms of radiation that we get, from x-rays to dental x-rays and etc., and then look at the next chart, it gives you a bit more of an idea. But just bear in mind, all this on this page equates to around 60 microsieverts. So as you can see, all of those blue elements in that first chart we looked at equate to just 3 on this chart, and we start to go into increased dosages. If we just add 2 more to that amount, so we end up with 5 little green blocks, it's approximate total dose received at Fukushima Town Hall over the 2 weeks following the accident. That's the equivalent to 100 microsieverts. So you put this into context with the the diagram that was just looking at, all in blue. If you're a pilot and you're regularly flying every day, long distant flights, then your exposure to this muons go up by a large factor. I'm surprised, although I can understand why airline companies aren't putting muon detectors in the cabins, because simply I don't think a pilot, after a year of flying and totaling up the amount of muons that had gone through his body while sitting in the cockpit of the plane, or the rest of the cabin staff for that matter, would probably want to do that job again, especially with the knowledge of the fact that this is on the increase, and therefore the risks are going to be on the increase. So if we just go through some of these, so obviously when we start to get into millisieverts, typical dose over 2 weeks in Fukushima, and then let's just have a look at a few others. So there's the on this right hand side here, the maximum dosage that is permitted for US radiation workers. That's 50 millisieverts, and then we start to go into the normal background dose. About 85% is from neutral sources. Nearly all of the rest is from medical sources. So if we now look at a more serious level of radiation, we can see that the fatal dose, even without treatment, is 8 sieverts. Usually fatal dosages are 4 sieverts. So if we are experiencing this equivalent in terms of muon radiation, you've already exceeded the fatal dose in relationship to standard radiation that we are aware of, such as alpha, beta and gamma. Muon radiation, if we can call it that now, is by far much worse, because like I said earlier on in this video, its density or mass and its speed at which it travels, it penetrates through a lot more material than the worst known radiation, gamma, beta and alpha, and for that reason it is far more dangerous. And if these things are on the increase, guys, then we really need to look into other areas of muons see how they can be deflected, and they can be deflected. We know that because it's just a matter of material above you that can slow them down, and if we can slow them down, then their life expectancy, even though it's relevant to the muon, is reduced. We know that this is the case. It can be reduced because of the experiment I was talking about yesterday in the video, where someone was in the 5th floor of the building. There was 10 floors in total, and he took it from the 5th floor to the basement and took a reading and reduced the muon counts by 30%. And I think if you can reduce it by 30%, you can also reduce it by a lot more. I don't think that there was layers of lead in between any of those floors, and lead is going to block out a lot more than concrete. And this is just some of the tests which we can do over the course of the research that we now gather on muons themselves. And we might have a better comparison table than what we've got now, but for now, guys, even the larger institutes are trying to effort the levels of danger. But what I can say already is that what they've already said and come out with and said is that cosmic radiation can be lethal in high quantities, and for that reason we know already that it can cause cancers of all sorts. It just depends on the exposure and the amounts as to how lethal the dosage is. And it's the same with any radiation. Like I say, I've had to just get this information to you guys. I've had to go through quite a lot of stuff, but the conclusion of all what I've looked at is that muons are in a different category of radiation compared to anything else that we have a standard for, and therefore a scale as a result. So if we are getting the same amount of muons as we are gamma radiation, then you could probably times it by a factor of 2 because of the nature of muons themselves. A few of the things that I've been looking at over the last 24 hours are how to categorise muons. Well, we can't categorise them as becquerels because becquerels usually measures the source of radiation, and we couldn't also categorise muons in the Gray's absorption dose, because Gray is usually a measurement of somebody who is lying in hospital with a certain amount of radiation per kilogram. And the reason why I've decided to closely categorize it with the civets is because it is a measure of effects on the human organs and tissues, as you can read here, and it's a measure of actual physical emitted radiation. So we're talking about an emitted radiation source. We're not talking about the source of where the radiation is coming from. We're certainly not talking about somebody lying in hospital with an amount of radiation poisoning. So that's why I chose the civet. So if we, like I say, just use the standard model of radiation poisoning or the radiation quantities, as in the case, then I think we just need to know that muon radiation is by far worse than gamma. And the reason why that is because simply muons are not stoppable by the same amount of quantity you would be able to with gamma. What I've come to realise over the last few days of just looking into all this information, and there's tons of it to go through, guys. You can easily kill 5 or 6 hours reading all the information upon muons and the research that's going on with them. Just for instance, you might not know that they are actually developing a muon X-ray scanning equipment, so that they can, because they know muons pass through very dense material and they can look deeper into structures. If they're looking for terrorists in bunkers deep down in the ground, then a muon detector or a muon X-ray machine would be perfect for that. It could also be perfect for searching oil deposits, gold deposits, mineral deposits, things like that. So you can understand why they want to use such things, and it's a wonder they haven't gone to the other end of the extreme and developed a muon bomb, because can you imagine the collateral damage that could be caused by that. It wouldn't surprise me if people in the military sector hadn't even pondered the idea. But there you go. Guys, like I said, we've opened a can of worms. We've just touched the surface. Yes, we've got a muon detector, and we're going to have a few more of those in the coming months built and possibly out there in the field detecting the amounts. But, you know, as far as I'm aware, you know, we've just opened up a can of worms now that is going to require us, in order to get better readings, more accurate readings, you know, we've got a lot more work ahead of us, and this needs to be done in a relatively short period of time, because if we are 4 to 5 years or 4 to 7 years away from, you know, a magnetic reversal taking place, then our magnetosphere is going to collapse down to about 10, maybe 5% of what it is right now. We've already lost, according to these organisations, 20% of the strength of our magnetic field already, our magnetosphere. And if that does go down in the next 5, maybe 6 years or so, you know, from 4 to 7 years, looking at the rate at which at the moment the main Canadian intensity or the Canadian pole is reducing, it could be around that point in time. In fact, you know, with what we're seeing right now, it is looking like, you know, the 40-degree mark is going to be the all-important point at where things really start to change, and that is when we enter those weak field lines and leave the strong field lines, as we've found in, you know, some of the experiments that we've conducted here. If that is the case, then, you know, this Earth is going to go through its reversal. As a result, the magnetosphere will collapse, and at that point in time we will be all adding to this, you know, in a grand solar minimum. And as a result of that, we will have a lot more cosmic radiation, and as a result of that, we will have a lot more muons coming down to the surface. These are byproducts of cosmic ray collisions high up in our atmosphere, and these are much worse than any of the known radiations that we've got at the moment. More worse than alpha, beta and gamma. Guys, I'll leave it here. You know, there's a link down there if you want to support us, you know, then you can do so on PayPal or Patreon, you know, but the main thing is that we don't stop. You know, there's a lot of work to do, and, you know, we're going to face this at some point, you know, and it's up to you if you want to, you know, get ahead of the game and, you know, inform yourself of some of the research and, you know, what comes out of this research. But, you know, it's like this, guys, you get first hand at it, you know, you don't get suppressed, it comes straight to you. And probably already what we've revealed over the last week with regards to what we have wouldn't have been allowed by some of these organisations. I bet it's new to you that there is even a far more formidable, worse radiation out there now that is interacting in our daily lives already, and is going to increase. That knowledge has come to you in the last week, and you know, that's big news. So yeah, guys, if you want to help support what we do, there's a link down there, and thanks for that, and thanks for those people that support us already on Patreon and PayPal. But guys, don't leave it to everybody else to do it. You know, we can't leave it just to a couple of people to support this. Okay, I'll say what I usually do. Have a good day, and as always, bye for now.